Assalamu alaikum. So in this video I will form this differential equation from this RLC circuit. So this is a second order linear differential equation with constant coefficients as a and b are constant. So what I will do in my video, in this video first I will form this differential equation and then I will solve it. So if you don't know any mathematical formulas to find the equation of I, that's no problem, because in this video I will use a Python code here and then I will make a graph. So let me erase all the thing because I will do it from the beginning. Okay, and if you are using any other languages like C++ or Java, it's okay. You just need to learn the algorithm, how I have done this, and if you learn the algorithm you can do that in which language, whatever you want. Okay, so let's start. First we need to make this equation. So let's say it's Vs. In this video I will take this as DC source, let's say 10 volt, but in the next, maybe 2 or 3 videos later, I will use a sinusoidal voltage here. That means a voltage that changes with time, and we will see what happens. But in this video we will apply DC source here, then R here, L, and then C. Okay, so now if I take a KVL in this loop, I will have Vs. The voltage across the resistor is IR if the current is I. Then the voltage across this inductor is L di by dt, and let's say capacitor's voltage is Vc. So let's write here Vc. Now you have to differentiate this term again with time, and if you do this you will find di by dt plus L d square I by dt square plus dvc divided by dt. Okay, so we know that the current through this capacitor's equation is I is equal to C, capacitor's voltage differentiated by time. So what is dvc by dt? It is simply is equal to I divided by C, right? Okay, so now let's rearrange this equation. L d square I by dt square, then R di by dt, and then 1 by Ci is equal to dvs divided by dt. And if I now divide this both equation, the left hand side and right hand side, by L, so let's divide this, divide by L, divided by L, divide by L. So this is my equation, and as in this video I am using a DC source, that means Vs is constant 10 volt. So if I differentiate it will become 0. So I have obtained a differential, a homogeneous equation, as there is a minus at the right hand side. That means the steady state current I doesn't depend on Vs, right? And it can be found by intuition that after some time this capacitor will become a open circuit, and that's why the current will become 0, right? Whatever the Bs is, ultimately the current should have to be 0. Okay, so I have found this equation. Now let's see what I will do in my code. So let's see what I will do in my code. So first I will take R is equal to 1k, C is equal to 47 microfarad, and L is equal to 25 millihenry, Vs is equal to 10 volt. Okay, and theoretically dt is tends to 0, but in my code I will choose dt is a small number, let's say 1 into 10 to the power minus 4 or 5 or 6, whatever you want. And as this is a second order differential equation, we know that we need at least two initial conditions. So let's assume that the initial current across this circuit is I0 is equal to, let's say, 0. That means when time is 0, the current is 0, and similarly the capacitor's voltage at time 0 is equal to, let's say, 1 volt. Okay, now I have to take initial conditions here. Okay, so initial current, so I have found that initial current I is 0 and initial capacitor voltage is, what is that, 1 volt, right? But no, there is no use of VC in my code here. I need to find the initial di by dt. So what is initial di by dt? To find initial di by dt, we need to write a equation across this inductor. Let's say the inductor voltage is VL. So VL is equal to LDI by dt, and VL can be written as Vs minus IR minus Vc. Okay, and as at t is equal to 0, oh, Vs is a DC source, right? So at t is equal to 0, t is equal to 1, to always Vs is equal to 10 volt, but I is changing, so we have to take the current at 0 time. Capacitor's voltage will also is a time function of time, so we need to take the Vc when time is 0, and if I do so, I will find di by dt at when time is equal to 0. So if I divide this equation by L, I will find this. So let's make this equation in my code. So in my code, let's name this a variable. Let's say the variable's name is di by dt, and this is equal to 1 by L Vs minus I. This I is the initial I, which is 0, right? So initial I is 0, then Vc, this Vc is the initial voltage, Vcu is equal to 1 volt. Okay, so thus I have find the di by dt. Now let's go to my for loop, and inside for loop, what I will do, let's modify this equation again. We can write d square I by dt square. Let's write d square I by dt square as like this. Okay, and now you have to multiply this equation. Oh, sorry. Now you need to multiply the equation by dt, and if you multiply the whole equation by dt, you will get d di by dt plus r by L multiply by dt will become di, then 1 by LC I dt. Is it right or wrong? Yes, it's okay. Really, it's okay or not? Okay, I think, yeah, r by L di 1 by LC I dt, okay, is equal to 0. And now inside the for loop, oh, what is this? di by dt, and in front it is d, so it is a small change, in di by dt, right? So let's write a variable d, then di by dt, and that will be equal to, what is the equation? Let's modify this equation. Di by dt is equal to minus r by L di 1 by LC I dt, right? Yes. So let's write this equation here, minus r divided by L R divided by L di. Oh, where is di? Okay, first let me write this equation, then I will say how to find di. I dt. Di is so easy. Where is di? So how can I find di, right? Okay, so what is, let's talk about this code here. This is my code, and I will make a rough here. Okay, this is rough. So di by dt, so this thing, okay, di by dt is equal to 1 by L this. That means di is equal to what? 1 by L. Okay, now wait, what is di by dt? Di by dt, I have make this as di by dt variable, right? And so what is di? Initial di is di by dt into dt. So I need di, and di is equal to di by dt into dt. So I have found a di, and yes, we have to update this di. Okay, we will do this inside this for loop, because di will not be same for the rest of the steps. Let me pause this video and see is there any error here. Okay, so I have checked and I found no error. Okay, so now what I will do, so it is the small change in di by dt. That means the di by dt, that means di, we will find a new di by dt, right? So initially this was di by dt, and after a small change I will find a new di by dt. That means di by dt, and after a small change I will get a new di by dt. Okay, now initially we have di, right? And then the di will be changed, and that will be equal to di by dt into dt. No, I think I made a mistake here. Wait, so no mistake, actually I was a little bit confused. No mistake, as di by dt is equal to what? Di by dt. So di is simply di by dt into dt. That means I will get a new di, which is di by dt into dt. And finally I will find a new I, right? As di is the change in current, so I plus di is the new I, and I will find new I. Okay, let's implement that in my code. Let's implement this in my code. Okay, what is this? Okay, let's erase this thing. So maybe I will need numpy, so let's import numpy as np, and maybe I need to plot, so import matplotlib dot pyplot as plt. Okay, so first of all, r is equal to 1k, L is equal to 25 millihenry, and C is equal to 47 microfarad, and dt is a small number, 1 into 10 to the power, that's a -4. Okay, then vs is equal to, let's say, 10. Initial I is 0. Initial capacitor voltage is 1 volt. Okay, now I need to make di by dt. So di by dt is equal to 1 by L into Vs minus I into R minus Vc. So di is equal to di by dt into dt. Now I need to make a for loop here for t in time, where time, what is time? Let's say time is np dot errands. Let's take time from 0 to how much? Let's say 100 millisecond. And what is the time interval? Let's say time interval is dt. So I will show the graph at 0, then dt, then again dt later. Okay, so inside for loop, first I need to make this di by dt. So di by dt is equal to minus R divided by L into di, R divided by L into di, then 1 by L into C I into dt, then di by dt is equal to di by dt plus di by dt. So I have update di by dt. That means I will get a new di, which is di by dt times dt, right? And I will get a new I, which is I plus di. Okay, so my code is done. Maybe I haven't made any mistake. Now to plot this equation, let's plot at x-axis we have time, at y-axis we have current. Now what is current? Let's say current is first an empty array, and we will fill up this empty array inside the for loop. So current dot append I. Okay, so initial I was 0, but it will gradually update itself. Then if you want grid, let's write true, and then pld dot show. Okay, let's run the code. Bismillahirrahmanirrahim. Oh, what is this? Maybe I have made some mistake. What is this? Okay, let me pause the video and find where is the problem. Okay, so actually my code was not wrong. Okay, I just decrease dt. I just decrease dt. Vc is equal to was 1 volt, right? Okay, let's take it 0 volt. And if I run this code, just for I have changed here just for 3 milliseconds, just to check what happens from 0 to 3 milliseconds. So I found a sharp increase in current, and then current is decreasing. Okay, so let's increase the time 30. No, okay, let's increase the time, let's say 300, and then now decrease dt to save time. Let's say it's -5, and now let's see what happens. Okay, so the current is decreasing. Actually the current is we can see a sharp increase in current, and then it's decreasing. So it's normal, right? Because um, okay, so initially when I apply this source, so when I apply this DC source, it will try to increase the current, it will try to drive the current through the circuit, so that's why the current was increases. And as we know that the capacitor will resist this current, and that's why the current is decreasing. Okay, now let's find the voltage of this capacitor. Okay, and to find the voltage across this capacitor, just what do we need? We know that Vs is equal to IR plus LdI by dt, so small LdI by dt plus Vc. So to find Vc, we have to write Vs minus IR, then LdI by dt. Okay, so we have to write this code now. So let's make voltage capacitor voltage is empty, and then let's make this equation. Vc is equal to Vs minus I into R minus L di by dt, and then simply write capacitor voltage dot append Vc. Okay, so let's see what happens. Let's start. Wait, so now we want to see the time versus want to see the time versus capacitor voltage. Okay, see if I run this code. Let's see what is the capacitor's voltage graph. Okay, so the capacitor's voltage looks like this. So it's increasing up to 10 volt. Okay, so what has happened here? Let's see, from 0 to just 1 or 2 millisecond. So for let's say 3 millisecond, and let's decrease the time interval, and let's see what happens there. Okay, so a sharp change. Okay, let's take it to 10 millisecond, and let's see what happens there. Okay, not 10, let's say 20. Okay, 20, then okay, let's decrease this to 5, and let's see now what happens. Oh, that means we need a small dt to operate at this region. Okay, we need a small dt. So if I decrease to -8, then if I decrease to -8, then I will get this. Okay, so I need a small dt to see the graph in this case for small time, but for later I can choose, let's say, 20 millisecond, and to see the voltages across all the time, let's say 20 millisecond, we need to reduce these dt's to save the time. But the problem is we can't have a perfect result in this case. Okay, but this voltage is trying to approach the battery's voltage 10 volt. Okay, so now let's try to find the voltage across this inductor. And to find the voltage across this inductor, what will you do? Let's say inductor voltage, and let's write here inductor voltage dot append. So what is the inductor voltage? Vs minus I into R minus the capacitor voltage. Okay, let's see. So let's take here inductor voltage. It will become zero. It will become zero at some time later. Wow, what happens here? It's so okay. So now we have to see the time. See at, let's say, 3 millisecond. So to see the graph at 3 millisecond, let's decrease dt to -8, and let's see how sharp it falls. Oh, okay, I understand. Now let's take it again smaller. Okay, so it's taking some time as I reduce the dt, but it should come. This is the duration of this video, huh? It's 26 minutes. Oh, okay, Ctrl C, it will not come. Okay, let's take -9. Why it's not coming? Okay, let's reduce the time. Let's say 1 millisecond, and let's see what happens. Okay, so I have a damping voltage here. Okay, that's all. Wait, let me my answer is right or wrong. Let's check that in a PSpice. Okay, so 1k 25 47 10, and initial condition, let's say 0, and here initial condition is 0. Let's say first I want to need the current. So if I run this code, I found a current here. Okay, let's compare this with my code. So if I take the current, okay, so this is my graph, right? Looks similar. Okay, now what is my code says? Let's say it's -5 or -7 from 5 milliseconds. Let's see what happens. Oh, okay, so this is my graph, and this is my code. So let's see, up to I have found up to 5 millisecond. So at 5 millisecond, I have a voltage of 8.99. okay, so at 5 millisecond I have a voltage of 8.99. yes, it's okay. Let's take some another point to see my code is right or wrong. Let's see, it's 20. Okay, so when 100 let's take up to 200 millisecond and reduce this dt. Oh, what is this? I need to make this dt smaller. Okay, so let's see when 100 millisecond at 100 millisecond we have 1.899. At 100 millisecond, oh no, our current is not at 100 millisecond, our current is doesn't match, so we have to reduce this dt again. So the main thing is the this dt. I understand the main problem is with this dt. We have to take smaller dt. So in 100 millisecond now it's no, yes, it's right, 118.112.1. So the moral of the story is we have to take a smaller dt.